uncertainty is added outside of the specification limits. So then this is the reason why R111 in mass says that if a weight is to belong to a particular class, its conventional mass should be within 2/3 of the maximum permissible error, because it's subtracting the guard band, the uncertainty. So the requirement by R111 is that the conventional mass is within 2/3 of the maximum permissible error, and the uncertainty is less than or equal to 1/3 of the maximum permissible error. Yes. Yeah, it depends. I guess uh, this is a specification of an instrument, so it's the relationship between the manufacturer and the person that's buying the instrument. Okay, typically that's the situation in metrology. However, it could be the relationship between the producer of the verification results and the user of the verification results. So, it's always a producer and consumer type of a relationship, and the amount of risk that's acceptable is, in calibration, is typically 5%, but it's upon agreement, really. I'm sorry, I didn't hear you. Can you repeat? Yeah. This is what this says here, because 17, I think this is what this says, that 17025 requires that whenever you make a conformity statement within a certificate, you have to state exactly which clauses of the standard or requirement are satisfied, okay? And you also have to state what decision rule you used in order to make the judgment of pass or fail. Okay, so this is a requirement of 17025 now. Yes, you need to have a procedure for how you decide, how you use uncertainty to decide conformity. There's information regarding this. You can find it in ILAC G8. So ILAC G8 has all of the necessary information for you to do, to write such a procedure. Yeah, Eurolab also, because this conformity assessment thing based on measurements is very, very important in testing. So it's not that important in calibration, but it's very important in testing. Okay, I have some examples here. Now, I don't know, how are we as far as time is concerned? Should I show you the examples and we leave the exercise for tomorrow morning when everyone is fresh? Or you want to do it now? I have no preference. What's that? It's covered So I have the examples and the practical. Okay. No, no, I don't know. It's not clear to me when we finish, but if people have the patience to listen to me, I'll speak. Okay, so one example that's, I think, very important to many labs because many labs are involved in balance calibration is the calibration of an analytical balance. Analytical, again, means a balance with a resolution of 0.1 milligrams. And typically, these instruments have a range of 200 grams. So I won't go into the details of this specific, I mean, it doesn't really matter. What I do want to show is the measurement model. So this is the measurement model that one uses in order to talk about um, modeling the measurement of the calibration of a balance. So the error is equal to the indication of the balance minus the mass of the reference standard that was used to do the calibration. Okay? So very simple model. However, each one of these terms can be analyzed further, and delta I is written like this, and M reference is written like this. So what are all these things? Delta I is the difference between IL and I0. That's the difference between the indication when the balance is loaded and empty. Plus we have 1, 2, 3, 4 terms which have zero value. Their expectation is zero. However, they do contribute to the uncertainty. So this is the limited resolution at the load, the limited resolution at zero, um, any eccentric effects that might show up because the mass is placed off-center, and repeatability. With regard to the reference mass that's used, this is its nominal value. This is the result from, so 1, 2, 3, 4. These are not all, well, it depends. I will assume that this is not, these are not zero, expectation zero. So values are can actually be determined. So this is the result from the calibration of this mass standard. This is my estimate of how this mass standard drifts from calibration to calibration. This is my estimate of the buoyancy correction when I'm doing the calibration. And this is my estimate of any convectional effects that might be present during the calibration of the balance. So if the weight is not at the same temperature as the balance is, then there will be convectional air currents which will alter the indication of the balance. The more accurate the balance, the more prevalent this alteration. And the uncertainty is just the uncertainty that's calculated from all of these, plus, well, the variance of the error is the variance calculated from all of these, plus the variance calculated from all of these. So I think that the people from EMI will find these very familiar. Anyway, so what are the different ways of estimating the uncertainty? So the uncertainty of limited digitization is 1/2 the resolution of the balance divided by the square root of 3. I think this is tip. So this is the uncertainty of the resolution twice. because we have the loaded state and the unloaded state. So this is the resolution divided by 2, divided by the square root of 3, because I'm assuming a rectangular distribution. Then for repeatability, just the standard deviation. And the uncertainty for eccentric loading, eccentric effects, is the maximum eccentric error divided by 2, divided by the maximum value of the balance divided by the square root of 3, because typically this is modeled as a relative value. You see then that the sum of all of these things is 1, 2, 3 terms which do not depend on the indication, and then a fourth term which does depend on the indication because this is a relative term. And why are we doing this? Because typically the eccentric error depends on how large the mass that I put on the balance is. The smaller the mass, the smaller the eccentric error. That's the reason. Okay, what about the contributions from the mass standard? Depending on whether I am using nominal values or the actual the values from the calibration certificate, then the uncertainty would be type B expanded uncertainty divided by coverage factor, k equals 2. Or if I'm using a nominal value, then it would be the maximum permissible error with a rectangular distribution. So it's divided by the square root of 3. So it's allowed in many instances because of the requirements of the particular calibration to use nominal values for masses instead of the actual values from the calibration certificates. So if someone does that, you have to make sure then that any errors that go uncorrected because of the way that you're doing things are included in your uncertainty. Okay, for buoyancy, there are two ways of dealing with it. Typically, depending on whether the balance is adjusted before the calibration or not, the balance is adjusted, then this formula can be, I mean, there are many ways of dealing with this, but this is the simplest way of doing it. It's probably an overestimation, but it's the simplest way of doing it, and I don't think that there's a need to go into more detail on this. So this has to do with, so it's a relative value, as you see, and it's the maximum permissible error divided by the nominal value, divided by 4, divided by the square root of 3. If the balance is not adjusted before calibration, I have to take into account any possible variation of the air density, so I have to include that in the formula also. Not that important right now. The drift, there's a way of estimating it. The relevant guideline says how to do it. A rectangular distribution is assumed. And the correction for convection effects, okay, the uncertainty associated with any mass errors due to convection, again, rectangular distribution. So then this is the uncertainty of the reference standard, or the variance, I should say, of the reference standard. So this is the variance of the indication of the balance, and this is the variance of the reference standard. So typically, when you're calibrating an instrument, that instrument also contributes to the uncertainty. Okay, it's not just the reference standard, but it's the instrument which also contributes. Okay, and this is what a typical uncertainty budget might look like for a balanced calibration. I don't want to go into all of the details, but you see here we have all of the contributions, and this is the sum of these contributions, this is the sum of those. Anyway, the thing is that it can be nicely handled by Excel. So Excel is the correct platform for doing these types of calculations and doing uncertainty budgets. Note that the effective degrees of freedom are calculated. So you see for low values of mass, there's only 19 effective degrees of freedom. For larger values of mass, there's 1,073. So this K value is pretty much equal to 2, whereas this is 2.14. So this has to be multiplied by this in order to get an expanded uncertainty with a confidence a coverage probability of 95%. Okay. Another example, again from mechanical metrology, the calibration of a digital pressure gauge using a deadweight tester. So we're only considering here one pressure value, 2 megapascal. Okay, and so this is the measurement model. So what does this say then? That the indication of the pressure device, okay, is equal to the generated pressure by the deadweight tester plus any difference in height between the two. So it's important to adjust for pressure head, plus any error that has to do with limited resolution of the instrument. So those are the important things. I don't want to go into those really. Here we have the total force that's applied on this area. So the total force is made up of the dead weights plus whatever force is applied by a buoyancy corrected piston, the buoyancy corrected force of the piston, plus any surface tension force that might be applied due to the surface tension of the oil. So in this case, the calibration certificate for the reference deadweight tester gives us these values here. So it's 32.2 parts per million for the effective area. And this is the distortion coefficient. I don't know if you're familiar with this type of a measurement, but the effective area is the area that's determined during the calibration of a deadweight tester or a pressure gauge. That's one parameter. And the other parameter is how much it distorts, the piston distorts, when pressure is applied to it. So we have different contributions to all of these input variables to my model. We have the drift of the effective area, which is 30 parts per million. We have uncertainties of the mass, of the masses used to produce to generate the pressure. We have the drift of the masses, which are used for this purpose. So the temperature contribution, because there's a dimensional aspect to this. The effective area is a dimensional quantity, so it depends on the temperature. We have the local acceleration due to gravity because we're calculating a force generated by dead weights. We have air buoyancy. We have from the buoyancy volume a contribution, small contribution. So what I'm trying to say is that a model can be to as much detail as is necessary for the particular calibration that you're doing. So if your calibration, as in this case, is has a required uncertainty, relative uncertainty of 100 parts per million, then you have to start considering all of these small um, contributions to the uncertainty. If um, the the uncertainty that is required is larger, then obviously some of these uncertainty contributions will not really uh, play any. The fluid head, type A, repeatability, uncertainty because the piston might not be totally vertical. It might have some angle to it. Rounding error due to the resolution of the digital display, DPI. And then this would be the uncertainty budget for this case. So again, Excel been just great. Okay, I'm running a little bit on these because I want to do the exercise now. Um, so let's do the exercise. These you can read by yourself, I think. You don't need my... So I had one more example. You can read it yourself. So let's take a look at the exercise that I have here. So one method for determining the density of a solid is by measuring the reduction of its weight when it's submerged in a liquid. According to the method, the body is weighed initially in air. The balance indication is WA. And then in a liquid, balance indication WL. The relation providing the unknown density in terms of the known liquid density at 20 degrees is given by this expression here. In this relation, there's a ratio of WL to WA, which is the indication in the liquid divided by the indication in air. And this is the ratio of the average balance indications resulting from n repeated measurements in air and in the liquid, while gamma sub nu is the coefficient of thermal expansion of the liquid.